This meeting is being recorded.
Right. Good afternoon. Is everybody doing okay? Are there any questions that I can answer before we start? Yeah? Yeah, there will be. It's on the syllabus, I think. There's like an entrance on that. We still need to work out the details and post them to you, but there will be a kind of a review session. And just to clarify, in case anybody has this question on their mind, the material that will be on the exam is everything up to today, included today. Okay, so not whatever we do for the rest of the week, but up till today will be on there. Okay, so let me know if there are any more questions. Today we'll continue with trees. But what we'll do is another generalization, and that is we will go to trees that can have arbitrarily many branches. Okay, so what we did, we kind of introduced these initial examples of trees like fruit tree and I think like a river system from what I remember, and a tournament. But each of those had at most two branches, right? We had a tournament example which only had a single kind of branch in one of the cases, but otherwise we had at most two branches. And one of the generalizations that we did was of trees was to allow arbitrary elements in the tree. So that's one way of generalizing tree. Another kind of direction where we can generalize is to allow arbitrarily many branches. So not just 2, but having 0, 1, 2, 3, 4, whatever there. And to do this, we will introduce another concept that is quite pervasive, or like another generalization of data types, and that is mutually recursive data types, or mutually referential data types. Okay. So the example that we will be working with today is something called S expressions. Has anybody heard this term before? Sorry? Homework that just came out? Okay. So S expressions, short for symbolic expressions, are kind of a data structure that you, before you read the homework that just came out, might not heard about before, but yet you were using them all the time. Okay. What S expressions are basically atomic data or lists of S expressions, roughly. Okay. So what I will do, I will start with the definition. We will define the atomic data, so kind of the data that these S expressions store. We will then define S expressions themselves as a mutually recursive data type. And then we'll see a few examples that I hopefully will make you kind of see how they relate to what we've been doing. Okay. So I said that S expressions can contain atomic data, so let me just define atomic data. Okay. Atomic data is simply any atomic data type in ISL or BSL. So can you give me the examples of atomic data? Yeah? Number, very good. Another, yeah? String. Yeah? Boolean. Any other? Yeah? Symbol, very good. Does everybody know what a symbol is? Okay. Oh, image. Image is another example that is kind of atomic, but it's not what we will consider here. But I do want to introduce symbols. So symbols are kind of the fourth basic atomic data type that we didn't really talk about. So I'll just do a brief introduction of symbols by examples. Symbols kind of look like strings on the surface, but they are not strings. Okay, a symbol is a piece of data that we introduce using a single apostrophe, and a string of characters after that. Okay, and this is basically a symbol. Now, what comes after the backtick is basically everything that you can use as a variable name in ISL or BSL. Okay, and they are very much related. A symbol is basically a representation of an identifier in ISL or BSL in the student languages, right? So every time I can do define a symbol, and underneath this a symbol is represented as a symbol called a symbol. Okay, it's a little bit abstract, but basically think of it as an opaque data type that we really cannot analyze much. What we can do is ask if something is a symbol. Okay, of course we'll return false for other data types. Okay, and the other important operation that we can perform is to compare symbols to one another. And that's about as much as we can do. They have no ordering, unlike strings, so we cannot make binary search trees of symbols. They don't have, we cannot find out the lengths of the symbols. They're just kind of unbreakable atomic data type that you can use as a tag or to refer to something. Okay, so think of them as kind of an internal representation of variable names or function names, and I will show you how this is possible. In fact, many of the library functions that we used, so for example from GDP image, right? When we had any function that took, let's do square 20, and we set solid and blue, for example, right? Using strings. These functions actually also accept symbols over here rather than strings. So I can express these functions just as well using symbols, because there are a limited number of possible variations, right? We don't really care whether there's a sorting between solid and outline or blue colors. Don't really need to have an ordering about them. All we need to do that is to be able to identify that this is solid and this is blue. Okay, and that's where kind of symbols are useful. But let's not spend too much time on it. All you need to know, symbols, you can check whether something is a symbol and you can compare a symbol to another symbol. Basically everywhere we've been using strings in our data definition, so like to identify an unknown, for example, you can use symbol in that place, okay? There are some reasons why you might want to. One is efficiency. It's much faster to use a symbol to represent certain things than strings, but this is for completeness more than a thing that you do need to use. Okay, so we have a data type of atoms. I won't be writing down the template just yet. I want to kind of now define the actual S expressions. So an S expression, S-expr for short, is one of, and an S expression is really just two things, one of two things. It's either an atom, okay, so any atom is automatically an S expression, or it's a list of S expression. Okay, so it's either an atom or a list of S expressions, and this is where the branching comes in. So we also simultaneously define what the list of S expression is. Okay. Since it's a list, it's either empty or we have a cons of an S-expr and a list of S expression. Okay. So this data type is equivalent to just saying this, but we do define a separate data type because we want to kind of emphasize the relationship between an S expression and a list of S expressions, and then the template of these two things. Okay. So this is our first what we call mutually referential or mutually recursive data type, where we are defining one data type that contains a list where the list contains a reference to the data type that we are defining. So they kind of complete each other, right? They refer to each other and complete each other. Before we do any templates, let's do a few examples. So, what are the simplest S expressions according to this definition? Yeah? Sorry? Number one, for example. Other examples of atomic S expressions? Yeah? An empty string, for example. Yeah, let's also do string containing something. Now, to distinguish, we can do the same thing as a symbol, but there are different data types, okay? So one has to be careful about these two are different. And let me do one Boolean one. How about some non-trivial S expressions? Any examples? Yeah? An empty list, yep. Okay. More interesting than that? Brendan? List of odd numbers. Yeah, that would be one. But we do have a problem that the list of odd numbers, if we take all odd numbers, it's infinite, so we kind of have to just do a limited one. Yeah? Cons one empty, okay, that's just a list of one. More interesting than that? Yeah? And an empty string, okay. Still not taking advantage of the power of these things. Yeah? List of foo-foo? Yeah, exactly. We can nest them, right? There are trees as well. So the list can contain other lists which are also considered as expressions. Let me do one more, say true and something like this. Okay. So the important feature here is that we consider this an S expression because each element here is an S expression, right? One is an atom. So a list of S expression is an S expression. So if we establish that everything in this list is an S expression, it is a list of S expressions. One is an atom, automatically an S expression. Here we have a list of things. If each of the elements are S expressions, then we have a list of S expressions, meaning that we have a S expression. A symbol is an atom, meaning it's an S expression. String is an atom, it's an S expression. So this is a list of S expressions. And if we apply the same rule to the rest of the list, right? So this is an S expression, this, meaning the list is an S expression, meaning this list is an S expression, meaning this list is a list of S expressions. Said so many times. That means that this top level list is also an S expression. Josh? Is there anything that you work with in this course that isn't an S expression? No. Everything you worked with is an S expression, and let me show you how. When you write down something like if equals, for example, x12, right? And then I do a function call to something in here, and I do maybe a more complex function call over here, and maybe something like this. on this side. Okay, so that's 1, 2. Wait, that's this bar and the if. Okay. So if I write an expression in BSL on ISL, it simply is an if expression. The way I can represent this is by representing it as an S expression, as a list of things. So we have a list here. We have a list of a symbol, which is the equals. That's also a valid symbol. The symbol X and the number 12. Then we have a list containing a foo and a 13. Then we have a list containing a bar and a list containing a plus symbol and 13 and 22. And a list of a minus and 1 and 2. Okay, so this is how S expressions relate to the actual syntax of the language that we've been using. Everything we wrote down is actually an S expression. Okay. Now, related to this backtick thing that introduces a symbol is a little bit more powerful than just introducing symbol names. Okay? Because I can take anything that's an expression in my language. So let me copy this thing. Okay. If I run it, it will fail because I have a lot of undefined variables here and functions. Wrong key press, sorry. But if I put a backtick in front of the whole thing, what I'll get back is exactly the list that I just wrote down. Okay, so this is just to prove that everything that we write down in our language is really just an S expression. Okay? It's just interpreted as actual programming constructs. This backtick in this position in front of an expression is what we call a quote. Okay, we won't dwell on it too much. If you are interested, just look up quote in the ISL documentation. You will find it there. You can also write it as the word quote instead of the backtick. But basically, what it is take this actually valid expression and convert it into an S expression representation. Okay. Okay. Yeah, exactly. So if I do empty, what I get back is an empty list, and the empty list is exactly just empty parentheses, but they need to be quoted. Okay, so it's exactly the same thing. Okay. All right. So, quote, very cool thing. Everything is an S expression. So let's try to write some templates for this data type. If I let's start with the atom. Okay, so we do need a template for an atom. Okay, what does this one look like? Brennan? Yeah, it would be a con with exactly 4 predicates. It's just an ordinary union data definition where, let me write this out. we either have a number, or we have a string, or we have a boolean, or we have a symbol. Okay. All of these are atomic data by the very definition. We don't know what to do about them, but the template of any atom processing function will kind of have this this shape. Okay. So I dealt with atomic data. Now let me make some room. What will the S expression template look like? Yeah? Cond, okay. And you want to say atom, huh? Sorry? You can use list, huh? So it's a predicate that we didn't use much, but it's available to us. So the next one would be list, huh? Okay. What do we do in each of these cases, Josh? Excellent question. Do we have a predicate if something checks if it's an atom? It's a data type that we just defined, right? So the answer is no, we don't have that predicate. So let's just write that predicate. When is this predicate true? Finn? Exactly. We have an atom if any of these are actually true. I'll just make it a little easier for myself. And so if we have a number, or we have a string, or we have a boolean, or we have a symbol, then we have an atom. Okay? So now we do have a predicate. The signature for this predicate is actually takes any data type and returns a boolean. Okay? Any is a special data type that basically contains all of the data types. So anything is an any. Okay. So we dealt with what? That. What do we do if we have an atom? Finn? Exactly. We have a template. It's a custom data type called atom template on this one, indicating that we want to call a helper function for atoms. The list case? Okay. I call what? List. So I need to define, we'll call it expert temple, and I made a mistake here. Okay. So we assume that here for the list we also define a template. This is just a simple list template, except so we either have an empty list of S expressions, or we have a cons of an S of a cons. What do we do in each of these cases in this template? It's not much to do for the empty case, right? We don't know, no info available. What do we do in the cons case? Josh? So I didn't hear all the details, but correct me if I'm wrong. So you suggested to call the S-expression template on the first of the list of S-expressions, right? Because the elements of a list of S-expression is an S-expression. We just defined the template for an S-expression, so that's what we need to call. And on the rest, we call the template that we are just defining recursively, and we are done. Okay. So this is our first mutually recursive data definition with mutually recursive templates, right? We have a reference to a list of S-expression which is defined below, which contains a reference to an S-expression which is defined above, which etc. The same thing happens, exactly the same thing happens in the template, right? Whenever we have a reference to a data type that we define, we just simply call the template for that data type. In that data type, when we define the template, if we have a reference to something that we already defined, we call that template. Okay? They just happen to be self-recursive. The main message here is if you follow the templates, follow the data definition to define the templates, and then follow the templates when you write the functions, you really cannot go wrong here. Okay? It's always just kind of making the mental step that I'm defining these at the same time. So I kind of for this to work, I rely on this one, and for this to work, I rely on this one. Okay, but once I wrote them down, they are there. Okay. Any questions about this mutually recursive definition? Okay, I will convert some of these examples that we wrote down here into some defines so that we can use them. Let's say foo. Okay, this one, then let's take this one. There was one nice one online. I'll just use that one. Good. I'll use food like this, and then list 1, 3, 5, 7. That's a good one. And uh, 6. Let me use this one. Okay. So a few examples to work with. Now let's define some functions on this data type. The first function, the first example of a function that I want to write down is design a function called flatten, which produces a list of all atoms in the given S expression. Okay. So taking an S expression, produce a list of all atoms in the given S expression. What would be the signature of this? Josh? So I take an S expression and I return a list of S expressions. Any other suggestions? Yeah? So I do want to take, so even the description says, produces a list of all atoms in the given S expression, so it does need to take in an S expression, right? And that's okay because a list of S expression is an S expression, so we handle that case. Yeah? Uh-huh. Should be a list of atoms, exactly. So there's, in theory, there's this signature fits, right? A list of atoms happens to be also a list of S expressions. So that's fine. But it's much less informative that way than if we write atoms, right? At some point we have to decide, okay, do we want the signature that's correct or do we want a signature that's correct and informative, right? Because any function can have this signature and we're good, right? But it's useless. So what we say here is we take an S expression and we guarantee a list of atoms. And we promise that you can rely on us that everything in this list will be an actual atom rather than an arbitrary S expression. Okay. Let's do a few examples. So, if I flatten S expression 1, what should I get back? Yeah? List 1, exactly. I have an S expression, it is an S expression, it contains an atom, the atom is 1, I need to return the list of all atoms, so it's just a list of 1. Okay. Sx per 3. Yeah? A list of simply just the symbol foo. Exactly. Let's do some more interesting things. What do I get back for this one? Pin? Yeah, exactly. S expression 4 is already a list of atoms that are contained in S expression 4, so what we get back is actually equivalent to Sx per 4. Okay, very good. Sx per 5. We get a list back. This one actually needs to do some work here. Brennan? Uh-huh. Yeah, 1, 3, 5, 7. Just list all the atoms in the order they appear. And the biggest one Max? Uh-huh. minus 1, 2. Did I get it right? Okay. Whew. Okay, so here are a few examples. Let's now. Are there any questions about the examples? Any of them doesn't make sense? Why the expected result is the way it is? Just want to make sure. Okay, so we are defining a function that takes in an S expression. So easiest thing in the world. Copy the template. And what do I do with the template? Yeah? I can do cons sexpr empty, okay, or even simpler, I can just say list of sexpr, okay. So even though the template dictates that we should use an atom template, right? If we would write down the atom function, what each of those cases would do is just like, if it's a number, just create a list of the number. If it's a string, just create a list of the string. So we kind of can simplify it. So the fact that we do have a template here doesn't mean that we always need to use the template. What should it prevent us from doing is kind of inlining the template and having a cont over the template. This case is really simple. We are simply returning a list containing the atom itself. How about the list case? Yeah? Exactly. So we do have this dictates a list expression template based function, which means we probably need a helper, which I will name flatten a list of S expressions, and I will write a stub for that one. Right. So I need a helper to help me deal with the list of S expressions. Let me write down the signature. Okay, this one actually needs to say I take in a list of S expression and return. What does it return? Yeah? List of atoms. Exactly, that's what we need. List of atoms. Now we do have a template for this one, so let's just copy it. Okay. If we have an empty list of S expressions, we have nothing to return. But what happens in the cons case? So we have an S expression, right? The first S expression, and then we have the rest of the list of S expressions. Each of them suggests a template, yeah? So we do have a function. We flatten the first, right? Here we call the function that we already implemented for flattening an S expression. First is an S expression. We do have a function for that. So we use that. And the remainder, just like with any odd list, we call the function itself, right? Now we have a list of atoms here based on the signature. We have a list of atoms here again, based on the signature. So what we need to do is simply append them together in the order they get produced. And we are done. All right. When we get to SX per 5, for example, to flatten this one, which is a list of S expression, we go straight to the list case of flatten. Flatten will take the first element, right? Flatten it, which will be just a list of the string good, and append that list of string good to the rest of the list, which will be the flattening of the list containing food, and then another list. So we had that one. So now we have two lists that will be appended eventually. Then we have another S expression that happens to be a list. So flatten LOSXper will dispatch to flatten, which then gets another list. So it will dispatch back. It will add all the elements there. We will get basically the same list back, but we then append it to the two lists that are over there. Let me run this, and we're good. Any questions about this function? Again, it's pretty much the same idea as a simple recursive function that just calls itself. But now we do that with two functions. And kind of the message again is follow the template, and it's unlikely that you will go wrong with the structure of this. Okay. Let's do an exercise here. Let's say that I want to define a flatten list of SXper. Okay, and I will call it version 2. Keep the same signature. But because I have a list of S expressions, I chose to use the template, but I might have as well used a list abstraction. Okay, it's still a list. So what would the function look like if we used a list? If we wanted to use it, define it in terms of list abstractions? Daniel, exactly. Well placed question. So Daniel asked, could we have used foldr instead of the list template? And the answer is yes. That's why I'm asking. How do we use it? So instead of using the template, we want to use abstractions to define this. Finn? So foldr append what? Yeah, so we do have probably want to use empty, but each element in the list of S expression is an S expression. So we don't know what to do when we want to append an atom. So this won't quite work. Any other suggestions with foldr? Yeah?
Takes in two values and does normal flatten on the first value, and then further depends on and also does normal flatten on the first value. Flatten this.
So it takes in one. So we have a list of S expressions. So the things that we have is an S expression, right? Then the rest here is kind of what I can call list so far, right? We pass in that's the lambda, this is something initial. I have the list of S expression, so each time this lambda is called, it will get an S expression, and then the list so far. Start with the empty one, and what do we do here?
So you do append the flatten on S expression, and then flatten list of S expression on the signal.
Like this. Josh? Yeah, exactly. Yeah. So Foldar will go through the list. What we get here is the list of already flattened S expressions, right? Calling flatten list of S expression would actually work on it, because a list of atoms is a list of S expression. We would just get the same list back. Okay. So what we can do is simply flatten the first S expression and append the list that comes from there to the list that we accumulated so far. Okay. Does it make sense? Here's a third definition that splits it into two things. So it might be easier to understand. So one thing I can do is to simply apply flatten to each element of the list of S expressions, right? Can kind of divide it into two steps. First, take the list of S expressions and give me all the atoms for each S expression. Once I have a list of lists, right, with atoms, I can append the list, each of those lists together to form my final list of S expressions. Okay, so those are two kind of alternative definitions. This one is more efficient because it only goes through the list once. Okay, this one first flattens each S expression and then appends them together, but they can be used interchangeably. Let me just check that we defined a good replacement, and we did. Okay. Any questions about this function? About the use of list abstractions? The point here is that even though list of S expression is kind of a part of the definition of S expression, it's still a list. We can still leverage the list abstractions there. We just need to be careful how we apply those functions. Okay, so I want to do one more example. That is, design a function which multiplies each number in the S expression by a given number. Okay, so I want a function that takes an S expression, finds each number inside of the S expression, and multiplies it by a given number. Let me call it multiply by what would the signature be? Brennan? Uh-huh. Right. Okay. It also needs to take in a number, right? I need to know the number that I'm multiplying by. So, very good. Let me just do these things. Okay. First example, really easy. I just have an atom. What I will get back is the atom multiplied by 2. If I do the same on an S expression that that doesn't contain an atom, whatever I do, what I get back that doesn't contain a number, I will just get the same thing back. Actually, I want to see the examples. If I multiply 3, let's say, sex per 5, what do I expect back? Brennan?
Would it still draw out the, like the string and the symbol and the...
So all it does is find each number and multiply those numbers, right? But it shouldn't do anything with the strings. So those will stay in place. It's a good question. So any non-numeric atom stays in place. What's the rest? Yeah?
3, 9, 15.
Okay, so we have a list of 3, 9, 15, 21. Okay, we go through the S expression. If it's not a number, we'll leave it be. If it's a number, we will multiply and preserve the structure of the S expression. Let's do the big one. So if I take this big one, oh gosh. All right, as I said, we preserve the structure, but we kind of look through, find every number and multiply it by 2. Let's make it a little explicit. And we have 2 here and 4 here. Okay. Make sense? What we are trying to do here? Brennan?
Where you have S expression 6, right, it's going to be a dash.
Yep, thank you. It looks awful lot like some kind of abstraction that we did multiple times. Finn? Yeah. Yeah, it's a map, but it's kind of restricted because we only apply to the numbers. And we are doing it over an S expression, right, for which we don't have a map. So all that's left to do is to actually define this. So we get a number and an S expression. We'll let the template lead the way. Okay. On the first glimpse, what will I need to do here? Okay. Actually, we will need to implement an Atom helper following the Atom template. So let me rename this by multiply Atom by the same number. Okay, and just like before, I will still need a helper for the list case. So I'll just start my little wish list here. Multiply list of S expressions by the given number. Okay. By and we should be good. The signature of this one is that it takes a number and an atom and returns an atom. Okay. We copy the template. To lead the way. What do we do in each of these cases? Yeah? Exactly. Actually, I want to call it an AT. So if it's, sorry, not in the string case. If it's a number, we multiply it not by 2, but by the number that is passed in, right? And otherwise, if it's anything else, we simply return the atom itself. There's nothing to do. We are only applying this adjustment to numbers. Okay? And that's exactly the reason why we do need to implement a helper, right? Because we treat each atom differently. Before, we just created a list containing the atom, whichever atom it actually was. But now we only treat numbers separately. So we do this. Now, here we have two choices again, right? We are dealing with a list. We can either use the template that we just defined, or we can use a list abstraction. Any preferences which we should use to define this? Josh? Can you speak up a little bit? So we want to map. So I guess we go with the list abstractions. We have a list of S expressions, and as we said, what we are doing here is awful lot like a map, right? We just do it over S expressions. One of the cases in S expressions happens to be a list, which means we can express the fact that we are just mapping something over by using the map, because all we need is to really apply it to each of the S expressions. Now, what is some lambda here? Yeah? So we need multiply. We have to use multiply exactly. But multiply by takes two arguments. So what we really need to do is to have a lambda that just takes an S expression, because that's what each element of the list is, and we need to multiply it by the given n. Okay. The n in here comes from the argument, because that's the n that we multiply every number with. The S expression comes from the argument to the lambda. We apply the lambda to each element, and we should be good. Let me run this and check whether we actually pass test, and we do. Okay, any questions? Yes? So Foldar needs a base case, right? Because we are accumulating, so you need something to replace the empty with. But in a map, we keep the empty, we keep the structure, and we build off of that. Any other questions? Okay, so we're out of time, so I just want to recap what the point here is. The point is that just like we have self-referential data, right? So we have data that's basically union data that just happens to have a self-reference inside of it. We can have mutually self-referential data where we have different data types that refer to each other to kind of complete the definition. The same way we have references in the definitions, we have recursive calls in the templates themselves, right, that kind of call each other. We saw a few examples with helpers for a list of S expressions. So, for example, in this case, we have a mutual recursion between multiply by, which relies on multiply list of S expressions by, and multiply list of S expressions by, which relies on multiply by for the S expression to process each of the arguments, right? The motivation for having this mutually recursive data was to have trees that can branch arbitrarily, right? Not just two, but basically having a list of self-references there. Kind of the message to take away: write down templates, follow the templates, and you'll be on the safe side of these things. Okay. So if there aren't any questions, then I'd like to thank you for coming, for participating. Have a good rest of today, have a good Tuesday, and I'll see you on Wednesday.